Okay, let's talk about ionization constant of acid. Ionization constant of acid or dissociation constant of acid basically give us the information about the strength of acid, that how much strong or weaker or moderately strong acid is. Let's drive how we can drive the ionization constant of acid in the same way that we did in ionic product of water. Here you can see the equation. Ha is representing the acid. As we know, acids are proton donor and bases are proton acceptor according to Bronsted and Lowry theory of acids and bases. So if the compound substance is donating acid a proton, that is acid, and the substance that is accepting the proton is base. So here you can see Ha plus water. This acid is releasing or donating its proton, and this water molecule will accept the protons and become H3O positive. By taking one proton, one hydrogen, it becomes H3. So H3O positive hydroxyl ion plus A negative. For example, it is HCl, so that A is this chlorine. Clear? So in the same way, for example, acid is H2SO4, so that A will be HSO4 minus. So this A is representing the other part. If you are releasing the proton, if the acid is releasing a proton, then the other remaining part is A. Let's write its chemical constant expression. Here you can see chemical constant expression Kc represent the equilibrium constant. As we know, equilibrium constant is equals to reactants, concentrations of products over concentrations of reactants, concentrations of product at the numerator and the concentrations of the reactant at the denominator. This is the chemical equilibrium expression. So by this expression you have to write the products at the numerator and reactants at the denominator. So products are hydroxyl ion and A negative. So here you can see the concentration of hydroxyl ion, the concentration of A negative. In a division, the concentration of acid and the concentration of water. In this reaction, we are taking water in excess. So when we are taking water in excess, very less amount of water is used to ionize the acid. So there is no major difference in the concentration of the water. So that's why water is considered as a constant. Initially and finally, there is a very less change in the amount of the water, in the concentration of the water. So that's why water is taken as a constant. So if we are taking water as a constant, so I am taking this water on the other side of equation. Here the water is in a multiplication division. On the other side of equation it will be in a multiplication with the equilibrium constant. Because equilibrium constant having a constant value and we are taking water as a constant, and this water will having a constant value because there is no measurable change in the concentration of the water. That is very small. That's why we are taking the concentration of water as a constant. This remaining equation is considered as a Ka. Ka is ionization constant of acid. Ka will be the concentration of hydroxyl ion. The concentration of H3O positive ion and the concentration of A negative ion divided by the concentration of the acid. This is not hydroxyl ion. OH is the hydroxyl. This is hydronium ion. H3O positive, the hydronium ion, A negative, and in a denominator, that is initial concentration of the acid. This is the ionization constant of acid because we are taking water as a constant and equilibrium constant as a constant value, because equilibrium constant at constant temperature remains same. We have discussed this point in this whole chapter of chemical equilibrium, that there is only thing which affect the equilibrium constant, that is temperature. If we are changing the temperature, the equilibrium constant will change, otherwise it remains same. So this is constant. We are taking the concentration of the water constant, that will be equals to Ka. Ka is the ionization constant of acid. A is representing here acid. So here you can see the expression for ionization constant of acid. Value of Ka of an acid give us information about the extent to which an acid can ionize. Greater the Ka, if the value of Ka is greater, then the greater will be the strength of the acid, which means the acid is strong. If the value of Ka is small, then the strength of the acid will be lesser, which means the acid is weaker. Here you can see, if the Ka is less than 10 raised to the power minus 3, then the acid is weak. If the Ka is equals to 1 to 10 raised to the power minus 3, then the acid is moderately strong. If the Ka value is greater than 1, then the acid is strong. So if in a question the value of Ka is equals to 1 to 10 raised to the power minus 3, then you can get the idea that the acid is moderately strong. If the Ka value is less than 10 raised to the power minus 3, for example, the value is 1.8 exponent 10 raised to exponent minus 5. So this is the smaller than 10 raised to the power minus 3. So it is showing that the acid is weaker. So in this way you can get the idea that the acid is stronger or weaker. This ionization constant of acid give you the information about the strength of the acid. Is the acid is stronger? Is the acid is weaker? Or is the acid is moderately strong? Any confusion till now? Amna, Manahil, Sabika, Taha, beta?
No, miss.
Okay. What is pKa of acid? As we have discussed about the pH or pOH and pKw. These are the negative log of H positive concentrations, negative log of OH negative concentration, and the negative log of Kw, ionic product of water. In the same way, pKa is the negative log of Ka. If the Ka is greater, the acid will be stronger. If the Ka value is lesser, the acid will be weaker. But opposite for pKa. In the same way, pH is greater, the acid will be weaker. The pH is higher, the acid will be weaker. The pH is lower, the acid will be stronger. So this is opposite. In the same way, if the pKa is higher, the acid will be weaker. If the pKa is weaker or lesser, the acid will be stronger. Let's talk about the difference between two acids. If there are two acids, for example, one acid 1, having a pKa 2 and the acid 2 having pKa 3. The difference of acid 1 and acid 2 pKa is 3 minus 2, that is 1. If the difference between pKa of two acid is 1, then the acid which having less pKa is 10 times stronger. Clear? Between two acids, if the difference of pKa, if the difference of their pKa value is 1, then the acid which having less pKa 2 is less than 3. So the acid which having less value of pKa is 10 times stronger than the second acid. If the difference of pKa of two acid is 2, difference of pKa value between two acid is 2, and the acid which having less value of pKa is 100 times stronger. Remember this, don't forget. If the difference of pKa between two acid is 1, then the acid which having less pKa value is 10 times stronger. If the difference of pKa between two values is 2, then the acid with less value of pKa is 100 times stronger. The next very important point in ionization constant of acid is percentage of ionization of acid. How we can calculate the percentage of ionization of acid and what is its importance? Before that, here you can see the table of different acids, their dissociation and their dissociation constant Ka and their relative strength. Here you can see HCl. HCl, as we know, is a very strong acid. If HCl dissociate into its ion H positive plus Cl negative, then its Ka value is exponent plus 7. Plus 7 is greater than 1 to 1 to 10 raised to the power minus 3. If the acid is stronger, the value of Ka is greater than 1, the acid is very strong. If the value of Ka is equals to 1 to exponent minus 3, then the acid is moderately strong. So here you can see the value of ionization constant or the dissociation constant of acid is exponent plus 7, which represent that this acid is very strong. In nitric acid, HNO3 dissociate into its ion as positive ion, NO3 negative ion, and the value of Ka, the ionization constant of this reaction, is exponent plus 3, that is greater than 1. Acid is very strong. If the acid is between the equals to 1 to exponent minus 3, then that acid is moderately strong. But here you can see that this value of Ka is very very large. 10 raised to the power 3 means that is 1000. So that's why this acid is very strong. H2SO4 dissociate into its ion as positive, HSO3 negative. The value of Ka is 10 raised to the power plus 2. So the acid is very strong. So in the same way, this whole table tells you about the strength of the different acids and their Ka values. Now we are going to talk about the percentage of ionization of acid. What is percentage? As we know, percentage, we can calculate the percentage by taking see here, percentage ionization of acid, amount of acid that is ionized, and initially available acid. So the total value, the total concentration that is initially present, and the amount that is ionized. So ionized acid, the value of ionized acid, the amount of ionized acid should be written at the numerator, and the total, the initial concentration of acid should be written at the denominator and multiply with the 100 to calculate the percentage of ionization of acid. In this way, you can calculate the percentage of ionization of acid. The percentage of ionization of acid give you the idea about that how much acid is stronger or weaker. The percentage of ionization of weak acid basically depends upon the dilution of that acid. According to Oswald's dilution law. What is Oswald's dilution law? The degree of dissociation of a weak electrolyte. These all are considered as electrolyte. These bases, stronger or weaker, acids, stronger or weaker, are said as electrolyte. Electrolytes dissociate into their ions when electricity passes from the electrolyte. So the degree of dissociation, that how much electrolyte dissociate, basically weak electrolyte, not strong. The dissociation of a weak electrolyte is directly proportional to the extent of dilution. If you are diluting the weak electrolyte, then its degree of dissociation will increase. For example, in a container, here is 100 centimeter cube of water, and you have added the 0.1 molar acid. The ionization constant, the percentage of ionization is 1.33%, which means 1.33 molecules out of 100 are ionized. But if you dilute this acid, if you are going to dilute 1.1 molar of acid into 1000 centimeter cube of solution, then its ionization percentage will increase, which means in this way now 13.3 molecules out of 1000 are dissociated. So when you increase the volume, when you increase the dilution, then there is the more chance for the ions to be ionized, for the electrolyte to be ionized, for the molecules to be ionized. If you increase the volume more than this, then more number of molecules of that acid will be ionized. So by the dilution, by adding more and more water, the chance for the acid to donate, to release its proton in a medium will increase. According to Oswald's dilution law, the degree of dissociation, that how much weak electrolyte will dissociate, is basically directly proportional to the extent of dilution. If you are adding more and more water, the dilution increase the chance of electrolyte to ionize, to dissociate into its ion. Greater the dilution, greater will be the percentage ionization. Remember that this is very important thing. If more water is added, then more dissociation chance will be increased. Here you can see the examples. First example is the same one as I have given here. Percentage ionization of 0.1 molar acetic acid is, for example, 1.33%, which means 1.33 molecules out of 100 are dissociated or ionized. If there is 1000 centimeter cube of solution, then 13.3 molecules will be ionized. So by dilution, more molecules will be dissociated. So in a second example, the percentage ionization of 0.00 molar acetic acid is 12.6%. We are taking the same acid but with the different concentration, 0.001 molar. That means the molarity is very low. So its percentage ionization is 12.6%, which means 12.6 molecules are dissociated out of 100. But if you are taking 1000 centimeter cube of solution, you are diluting the solution, you have added more water, then 126 molecules are dissociated. Here you can see the concentration is 0.1 molar, and here you can see the concentration is 0.001. So this is more diluted solution as compared to this one. That's why its percentage ionization is greater than the first example. So if the molarity is lower, if the molarity is lesser, which is showing that solution is diluted. So if the molarity is lower, the solution is diluted. The chance for the electrolyte to ionize is greater. In the same way, if the molarity is higher, the chance for the electrolyte to ionize will be lesser because there is less dilution. So remember, if the weak electrolyte is there, this is not for a strong electrolyte, this is for a weak electrolyte. If you increase the concentration, decrease the concentration by adding more and more water, then its ionization, its dissociation into its ion will be increased. In this table that is in your book, here you can see the different molarities, the different concentrations of acetic acid, how much the percentage ionization for the acid, and their Ka values. Next topic is ionization constant of bases. Acids are proton donor according to Bronsted and Lowry theory, and bases are proton acceptor. So ammonia is considered as a base. When we add the ammonia in a water, water will lose its proton and ammonia will take that proton. Water is amphoteric, it behaves as an acid or a base according to the situation. So in this situation, this ammonia is behave as a base, it will accept the proton, and water behave as a acid. So water will lose its proton and ammonia will take that proton and becomes ammonium ion. Here you can see carbonate. This carbonate will take the proton from the water and become bicarbonate, and hydroxyl ion will be released in the medium. So bases accept the proton and acids donates the proton. So if we are going to write the journal equation, B is representing a base, water will lose the proton, the base will accept that proton, and OH will be released in the medium. Write its equilibrium constant expression, products at the numerator, reactants at the denominator. In the same way, water is taken as a in an excess, that's why water is considered as a constant. So water is constant in this reaction because water is taken as a in an excess amount. So there is not measurable change in the concentration of the acid. So here the water is in a denominator. On the other side of equation, it will be in a multiplication with the equilibrium constant. This whole expression is Kb, ionization constant of base. Ka is representing ionization constant of acid, Kb is representing the ionization constant of base. So ionization constant of base is concentration of BH positive, concentration of OH negative, and divided by the concentration of the base, that is initial concentration of base. Kc is a constant, the amount of the concentration of the water is constant. This is ionization constant of bases. Here you can see the dissociation of some of the bases and their ionization constant value and their strength. Here you can see sodium hydroxide ionize or dissociate into its ion Na positive plus OH negative. Its Kb very high, that's why its strength is very strong. KOH dissociate into K positive and OH negative. This acid is also very strong. That's why its value of Kb is very high, greater than 1. Calcium hydroxide is high and a strong acid, its value is high, not very high. Ammonium hydroxide, so here you can see the different acid with the different Ka and with the different strength. aniline, methylamine, these are weak acids. In the same way as we discussed in Ka, if the Ka value will increase, the acid will be stronger acid. In the same way, if the value of Kb will be increased, then base is stronger base. But opposite for pKb. pKb is the negative log of Kb. In the same way, pH, pOH, pKw, pKa. The negative log of all these are opposite. If the pKb value increased, if the value of pKb is high, then acid is weaker. If the pKa value is lesser, then the acid is stronger. If the difference of pKb between two bases is 1, then the base with the smaller pKb is 10 times stronger than the other. As we have discussed in ionization constant of acids, if the difference of pKa is 1, then the acid with the smaller pKa is 10 times stronger. In the same way, the difference of pKb, the negative log of Kb, the difference of pKb is 1, then the base with the smaller pKb is stronger. How much time? 10 times stronger. Here you can see example number 4 from your book. Open your book and see ionization constant of acetic acid is asked, moles per dm cube is given, and here you can see the equation. Acetic acid ionized into its ion, acetate ion and proton, hydrogen ion. The Ka value for this reaction is 1.85 exponent minus 5. Initial concentration of acetic acid is 0.1 moles. And initially, as we know, there are 0 moles of products. After some time at equilibrium, some of the concentration of acetic acid is used or converted into its ions. So 0.1 minus x. This x is the concentration of the product. X mole of acetate ion and x mole of hydrogen ion. So this x is very small because acetic acid is very weak acid and weak acid dissociate very less. So if this weak acid ionized in a very small amount, then this x is considered as a negligible. So the whole term, the whole value is considered as approximately equal to 0.1. Maybe this x is 0.0001. So this value is very small. We can neglect this value. That's why the ionization of acetic acid may be very less. So that's why, because of its weak nature, acetic acid is very weak. It dissociates very less. Only 5% weak acids ionized. Only 5% out of 100. So weak acids having a very less ability to ionize. So that's why it is considered as 0.1. So write the equilibrium constant expression for acid. Equilibrium expression, as we know, as water is always taken as an axis, so that's why no need to write that. And Ka expression for acid is products over reactant. Product is represented as X, acetate ion is represented as S, proton is represented as X. Concentration of acetic acid is 0.1. At equilibrium, that is 0.1 minus X, but that is approximately equal to 0.1 because X is very small. So that's why we are taking it 0.1. Xx becomes X square. Ka is given in an equation, that is 1.85 exponent minus 5. 0.1 is in a division. On the other side of equation, it will be in a multiplication. So 1.85 exponent minus 5 multiply with the 0.1 x square. Take under root on the both side. X will be cancelled out with this square root. And the square root of 1.8 exponent minus 6 will be 1.3 exponent minus 3. This is the value of x. This is the value of x. So this x is basically the concentration of the protons and or the concentrations of the acetate ions. Here you can see we get the concentration of the H positive ion. That how much protons are released by the acetic acid. This is the amount 1.3 exponent minus 3. So we have to calculate the percentage ionization. So according to the formula, the concentration of the ionized acid, to how much acid is ionized? 1.3 exponent minus 3. So here you can see 1.3 exponent minus 3 on the division original concentration of acid. So originally acid is 0.1 mole per dm cube. So divide these terms, multiply with the 100, you will get the percentage ionization of acetic acid which having a molarity that is 0.1, having a percentage ionization that is 1.3. So which is representing that 1.3 molecules out of 100 are ionized and 13 molecules are ionized out of 1000. Clear? By this you can calculate the percentage ionization of different acids and get the idea about their strength, that how much acid is strong and how much acid is weaker.